Hello, everyone. So before we start doing stoichiometry problems, I would like to remind you guys what we should actually do. So given the chemical reaction where A and B are reactants and C and D are products, that is A plus B is C plus D. And given the amount of A in grams, we can find the amount of C in grams in the following. So we have the mass grams of compound A. So in order to find the moles of compound A, we would need to use molar mass grams per mole of compound A to get the moles of compound A. Then we would need to use the mole ratio of A and C from balanced chemical reaction to get the moles of compound C. And then we would need to use molar mass or grams per mole of compound C to get the mass grams of compound C. So we can try doing this with a specific example. An ammonia NH3 can be synthesized by the reaction 2NO plus 5H2 equal to 2NH3 plus 2H2O. How much ammonia is produced when there are 86.30 grams of nitrogen monoxide? And then we also need to find how much ammonia is produced when there are 25.60 grams of hydrogen gas. So let's start with 86.30 grams of nitrogen monoxide. We would need to convert it to moles of nitrogen monoxide from grams of nitrogen monoxide. So for 1 mole of nitrogen monoxide, we would have 30.006 grams of nitrogen monoxide, and the 30.006 grams of nitrogen monoxide represents the molecular weight of nitrogen monoxide. And so we would need to convert that mole of nitrogen monoxide to mole of ammonia by looking at the balanced chemical reaction. So we can see here that for each 2 mole of ammonia, there are 2 moles of nitrogen monoxide. So right now we have the amount of moles of ammonia. And so we would need to convert it from moles to grams. So the ratio from grams to moles of ammonia is 17.031 grams of ammonia over 1 mole of ammonia. And by using your calculator, we would have 48.98 grams of ammonia. Now for hydrogen gas, we would need to convert grams of hydrogen gas to moles of hydrogen gas. So for each 1 mole of hydrogen gas, we would have 2.016 grams of hydrogen gas. And the 2.016 represents the molecular weight of hydrogen gas. And so right now we have the moles of hydrogen gas, but we would need to convert it to moles of ammonia. So for 2 moles of ammonia, we would have 5 moles of hydrogen gas. And then we would also need to convert from moles of ammonia to the grams of ammonia. And the ratio for that is 17.031 grams of ammonia over 1 mole of ammonia. And by using our calculator, we would have 86.51 grams of ammonia. So that's basic stoichiometry. Next, I want to talk about the limiting reagent. So by definition, limiting reagent is a reactant that is used up in the reaction. And it is also a reactant, in other words, it is a reactant that is completely consumed in a chemical reaction and limits the amount of product. And the excess reagent is any reactant that occurs in a quantity greater than is required to completely react with the limiting reagent. So think of the limiting reagent by the following. We can make 1 pizza by having 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese by assumption. By forming a chemical reaction, we would have the following: 1 crust plus 5 ounces of tomato sauce plus 2 cups of cheese is equal to 1 pizza. So the 3 ingredients in here represents the reactant and the pizza represents the product. Suppose that we have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce. How many pizzas can we make? So we have enough crust to make 4 pizzas. So by doing this, we would have the initial crust, which is 4 crusts, and then we would want to convert it into pizza by looking at the balanced chemical reaction. So for every 1 pizza, we would have 1 crust, and the result, we would have 4 pizzas. For cheese, we would have enough cheese to make 5 pizzas by doing the same thing as the previous one. And then for tomato sauce, we would make enough pieces of 3 pizzas. So what do these numbers mean? The tomato sauce is the limiting reagent, since we can only make up to 3 pizzas, knowing that we will use all 15 ounces of tomato sauce. And the crust and the cheese are the excess reagent, since we still have more crust and cheese to use, even though we use all 15 ounces of tomato sauce. So let's go to a specific example. For the reactions shown, find the limiting reactant for each of the initial amounts of reactants. So we have 2 sodiums and bromine gas is equal to 2 sodium bromide. So for the first problem, we would have 2 moles of sodium and 2 moles of bromine as the initial. And to find the number of moles in the product, which is the sodium bromide, we would need to convert from moles of sodium to moles of sodium bromide. So we would have 2 moles of sodium as the initial, and for every 2 moles of sodium bromide, we would have 2 moles of sodium coming from the balanced chemical equation, and we would have 2 moles of sodium bromide. So pretty simple. And for 2 moles of bromide, we would multiply it by the ratio from the balanced chemical equation. So for every 2 moles of sodium bromide, we would have one mole of bromine. And the result is 4 moles of sodium bromide. So the limiting reagent, again, the definition of limiting reagent is a reactant used up in the reaction. The reactant that is completely consumed in a chemical reaction and limits the amount of product. So between these two, we would suggest that the 2 moles of sodium bromide represents the limiting reagent. So specifically, sodium is a limiting reagent because we used all of it, all of the sodium. And the bromine is the excess reagent because we still have extra bromine, even though we used up all of the sodium. Now, the next problem. So the initials of the following reactants are 1.8 moles of sodium and 1.4 moles of bromine. So we would do the same thing as the first problem. So we have 1.8 moles of sodium, and we would use the same ratio from the first problem. So for every 2 moles of sodium bromide, we would have 2 moles of sodium, and the result is still going to be 1.8 moles of sodium bromide. Now for the next initial amount, which is 1.4 moles of bromine, we would still use the same ratio as the first one. So now we would have 2 moles of sodium bromide for every 1 mole of bromine. And the result is 2.8 moles of sodium bromide. So now again, the limiting reagent is sodium because we use all of it. We use all of the sodium, and the excess reagent is the bromine. Now the third problem, we were given the initial amounts of 2.5 moles of sodium and 1 mole of bromine. And now we would do the same thing again, 2.5 moles of sodium multiplied by 2 moles of sodium bromide over 2 moles of sodium, so that we can get 2.5 moles of sodium bromide. Now for 1 mole of bromine, we would do the ratio again to find the number of moles in sodium bromide. So for every 2 moles of sodium bromide, we would have 1 mole of bromine, and now we have 2 moles of sodium bromide. So now, this time, the bromine is the limiting reagent and the sodium is the excess reagent. And now the fourth problem gives us the initial amount of 12.6 moles of sodium and 6.9 moles of bromine. So again, we would do 12.6 moles of sodium and we would do the ratio, which results in 12.6 moles of sodium bromide. And now for bromine, we have 6.9 moles and we would do the same ratio, which results in 13.8 moles of sodium bromide. And now we can say that the sodium is the limiting reagent because it has less moles of sodium bromide than the second one, which is 13.8, and the bromine is the excess reagent. Okay, now let's talk about the percent yield. Now, the theoretical yield is the amount of product that would result if all the limiting reagent is reacted. And the actual yield is the amount of product that is actually obtained from a reaction. So now the percent yield is calculated as the actual yield over the theoretical yield multiplied by 100%. So going back to the pizza example, the limiting reagent is a tomato sauce, which it can only produce 3 pizzas along with the crust and cheese. However, we only ended up making 2 pizzas. So we can say that the actual yield is the 2 pizzas and the theoretical yield is the 3 pizzas. So by calculating the percent yield, by plugging in the appropriate numbers, so percent yield equals actual yield over theoretical yield multiplied by 100%, which equals to 2 pizzas over 3 pizzas over 100%, which would be 66.67%. So just a note out there that the limiting reagent of the compound will always be less than or equal. The limiting reagent of the compound will always be the theoretical yield, and the actual yield is always equal or less than the theoretical yield. Okay. So by having all of these information, we can combine them into these specific problems. So a urea, which its chemical formula is CH4N2O, is a common fertilizer that is synthesized by the reaction of ammonia, which is NH3, with carbon dioxide, given that the balance chemical equation is right here. 2NH3 plus CO2 equals CH4N2O plus H2O. In an industrial synthesis of urea, a chemist combines 136.4 kilograms of ammonia with 211.4 kilograms of carbon dioxide and obtains 168.4 kilograms of urea. Determine the limiting reactant, theoretical yield of urea, and percent yield for the reaction. So, solution for this, we can start by finding the limiting reactant with the given amount of the reactants, which is 136.4 of ammonia and 211.4 kilograms of carbon dioxide. So let's start with 136.4 kilograms of ammonia. So that is already given. Now we want to convert kilograms to grams. So for every 1,000 grams, we would have 1 kilogram. So we have grams of ammonia in this case, but we would need to convert from grams of ammonia to moles of ammonia. So the ratio of that is for 1 mole of ammonia, we would have 17.031 grams of ammonia. Now the 17.031 grams of ammonia represents the molecular weight of ammonia by adding the atomic mass of each element and the corresponding number of the elements. And then now for this, in this case, we have the moles of ammonia, but we need to convert from moles of ammonia to moles of urea by looking at the balanced chemical equation. So the ratio for urea to ammonia is 1 mole of urea for 2 moles of ammonia. Now we have the moles of ammonia, moles of urea. We would then need to convert from moles of urea to grams of urea. So for 1 mole of urea, we would have 60.182 grams of urea. And now we would need to convert it from grams to kilograms, because that's what we want. So for 1 kilogram, we would have 1,000 grams. And the result would be 241.0 kilograms of urea by plugging in the calculator. So now we have found the amount of urea by using 136.4 kilograms of ammonia. Now we would do 211.4 kilograms of carbon dioxide. So we would start the given, and then we would need to convert again from kilograms to grams. So we would do the same thing as the previous one, and we would do a similar thing, what's that called? Similar conversion from the previous one. So now we have the grams of carbon dioxide. Now we would need to convert from grams to moles of carbon dioxide. So this is the ratio: 1 mole of carbon dioxide for 44.009 of carbon dioxide. But we would then need to convert it from moles of carbon dioxide to moles of urea. And by looking at the balanced chemical equation, the ratio for that is 1 mole of urea for every 1 mole of carbon dioxide. And then we would need to convert from moles of urea to grams of urea, which is this one. And we would then need to convert it from grams of urea to kilograms of urea. And by plugging the calculator, we would have the total of 289.1 kilograms of urea. So now, by definition of limiting reagent, the lower value of urea, depending on the amount of each reactant, is the limiting reagent. So the limiting reagent in this case is ammonia with 241.0 kilograms of urea, which also means that 241.0 kilograms of urea is the theoretical yield. The actual yield of urea is 241.0. No, it's not. Okay. The actual yield of urea is actually 168.4 kilograms of urea, since it is already obtained in the problem. So this is a formula of percent yield. So the actual yield, again, is 168.4 kilograms, and the theoretical yield is 241.0. Sorry about the typo. Yeah. So by identifying the actual yield, it's already given in this part. Okay. So now the percent yield for this reaction is 69.88%. Okay. Now the second problem in here, so we were given that many computer chips are manufactured from silicon, which occurs in nature as silicon oxide. When silicon oxide is heated to melting, it reacts with solid carbon to form liquid silicon and carbon monoxide gas. In an industrial preparation of silicon, 155.8 kilograms of silicon oxide reacts with 78.30 kilograms of carbon to produce 66.1 kilograms of silicon. Determine the limiting reactant, theoretical yield, and the percent yield for this reaction. Now, in the previous problem, we were given the balanced chemical reaction, but in this case, in this specific example, we would need to make our own balanced chemical equation. So the solution for this is that the following balance of chemical reactions should be like this, because it says here in the problem that when silicon oxide is heated to melting, it reacts with solid carbon. So those are the reactants. And it says to form liquid silicone and carbon monoxide gas, meaning that the silicon and carbon monoxide gas are the products. But in this case, it's not really balanced because in the reactant side, we have 2 oxygens, but in the product, we only need 1. So in order to balance it, we would need to add a coefficient of 2 in the carbon monoxide side in the products and 2 carbons to balance it out. So now we have this balanced chemical reaction in this case. So to find the limiting reagent, whether it's silicon oxide or carbon, we would need to convert from kilograms of silicon oxide to kilograms of silicone and kilograms of carbon to kilograms of silicone. So let's start with 155.8 kilograms of silicon oxide. So first we would need to convert it again from kilograms to grams. So for every 1,000 grams, we would have 1 kilogram. But now we would need to convert it from grams of silicon oxide to moles of silicon oxide. So for every 1 mole of silicon oxide, we would have 60.084 grams of silicon oxide. Now the 60.084 grams represents the molecular weight of the silicon oxide. So right now we have the moles of silicon oxide, and we would need to convert from moles of silicon oxide to moles of silicone. So by looking at the ratio in the balanced chemical equation, we would have 1 mole of silicone for every 1 mole of silicon oxide. So now we have the moles of silicone. We would then need to convert it from moles of silicone to grams of silicone by doing this ratio, 28.086 grams of silicone for every 1 mole of silicone. And then we would need to convert it from grams of silicone to kilograms of silicone. So for every 1 kilogram, we would have 1,000 grams. And by plugging in the calculator, we would have 72.83 kilograms of silicone. Now we would do the 78.30 kilograms of carbon to see if the result kilogram of silicone is higher or lower than the 72.83 kilograms of silicone. So now let's start with a given 78.3 kilograms of carbon. We would need to convert it from kilograms to grams like this. And then we would need to convert from grams of carbon to moles of carbon. So for every 1 mole of carbon, we would have 12.011 grams of carbon. So now we have moles of carbon. We would now need to convert it from moles of carbon to moles of silicone. So by looking at the balanced chemical equation, the ratio of silicon to carbon is 1 to 2. So 1 mole of silicone for every 2 moles of carbon. And now we would need to convert the moles of silicone to grams of silicone. So 28.086 grams of silicone for every 1 mole of silicone. And we would need to convert that gram of silicone to kilograms of silicone by doing this, 1 kilogram over 1,000 grams. And by plugging in the calculator, we would have 91.55 kilograms of silicone. Now, the limiting reagent in this case is the silicon oxide with 72.83 kilograms of silicone because we would use all of the silicon oxide. And even though we use all of it, the excess reagent is carbon, because even though we use all of the silicon oxide, we still have the remaining carbon in the reaction. This also means that the 72.83 kilograms of silicone is a theoretical yield, and the actual yield of silicone is 66.10 kilograms since it is already obtained in the problem. So now we would need to calculate the percent yield. So percent yield equals actual yield over theoretical yield times 100%. And by plugging in the right the right numbers. So 66.1 kilograms of silicone is the actual yield, and 72.83 kilograms of silicone is a theoretical yield, which results in 92.76%. And which means that this is just a percent yield for this reaction. Sorry, I meant to write this as 72.83. And again, from the previous example, this is not the actual yield, but the actual yield of urea is 168.4 kilograms. And I guess that's it. Thank you. Thank you very much. There.